Okay, I think we can start. My name is Krzysztof Gogolewski. I've been working at Twig on implementation of linear types for the past half year. It is a really exciting adventure, and today I'll talk about linear types. There are many ways you can add linear types to a language, and I'll focus on the one that was added as a GHC proposal, the one that is known to be backwards compatible with the existing Haskell language. So let's start. If you'd like to follow along, there is a Docker image. The alternative is you can clone the repository github.com twig.ghc. However, then you would have to build GHC, which will take you probably an hour. So I would not. If you haven't done that already, I do not recommend doing that now. Let's start working. So here is a normal identity function. Linear types give you a new identity function, give you a new function type that is currently written as arrow dot. However, the syntax is only temporary. It remains to be seen what will be the final syntax. This is only a prototype syntax. And if you'd like to use it, you need to enable linear types extension. The alternative is to use a lollipop symbol, which looks like that. This symbol comes from linear logic, and if you'd like to use it, you also need Unicode syntax. A linear function is written the same way as a normal function, except there are some restrictions on what you can do. A linear function must consume its argument exactly once. What does it mean? I will explain. For now, you can notice that if I try to just ignore the argument, I will get a compilation error. If I try to duplicate it, I'll also get a compilation error. A linear function can do several things. Given a linear argument, it can be passed unmodified, like this one. It can be passed to a different linear function. So if I write, I can say fx equals identity of x. You can wrap the linear argument in an algebraic data type. For example, I can say x0. If it's a function, you can call it only once on a fixed argument. So I can say a to int, oh, sorry. Furthermore, you can do a case split. So if I have a Boolean argument, I can pattern match. I can do pattern matching, and all clauses have to use linearity in exactly the same way. So notice that in a sense this x appears in the function definition twice, but the function is still linear. In normal Haskell, you can the more arguments you have, the more things a function can do, right? Because you have more things in the context. With linearity, an argument can be a liability. You have to use it. Otherwise, the function won't type check. So if I have a constant function, this type checks, I can make it linear in A, because I'm using x linearly. But if I make it linear in B, I'm getting a compilation error, and there is no way to fix it except by saying some nonsense like giving a loop.
Question. When we did the pattern matching, so I assume if we tried to use the Boolean in any other way, we wouldn't be able to make the function linear, right?
So what you can do is you can do anything you like with non-linear arguments. You can pattern match on them. You can also pattern match on a linear argument. In this case, you have to consume all fields linearly. I'll get to this. Just a second.
What happened with the bank patterns and linear signatures?
You can have a bank pattern. and it doesn't have linearity at all. So I can do this, except I need to. Oh, and I need.
Yes, okay.
Right, so this works. I'm sorry, I need to walk outside for a minute to take a bit of refresher. I'll be back soon. Słabo się czuję.
Okej, mogę jakoś ci pomóc? Chcesz się położyć? Połóż się może. Krzysiek, weź nogi wyżej głowy, żeby ci krew nie leciała, jakby wiesz, ten, i położysz się tutaj. I się połóż. To jest słabo, weź mu przytrzymaj. Przytrzymaj mu nogi, żeby mu jeść ten. Tak, wodę. A ja cię z tego słońca. Dobra, to ja cię przysunę, a ty odpoczywaj. Spokojnie, jest okej. Jest okej. On jest ratownikiem. Ja dużo razy zemdlałam, także wszystko jest pod kontrolą. Nie, już jest lepiej. Już zaczynasz mieć kolor człowieka. Wszystko jest dobrze. Ewentualnie wszystko elektrolitu. Apteka przecież, tak. A jest się zamknięte wszystko.
Znaczy ona jest 24 godziny.
Czujesz się już lepiej?
Myślę, że tak.
Ale czujesz się bardziej odwodniony, czy jak
Chyba
wstałeś?
było brak tlenu czy coś.
Jak wstałeś jest okej teraz? W sensie nie zrobiłeś
Jest
się
lepiej,
ciemno
tak.
jak wstałeś? Dobra. No to super.
Okay, sorry. So regarding bank patterns, in normal Haskell you have a primitive sec that works this way, and in fact you don't need bank patterns. You can always use the function sec. However, with linear types, sec is not a linear primitive. It is just ignoring x. And if you would like to have a correct linear primitive that would supersede linear, that would be equivalent to bank patterns, you can't use this version of sec. What you need is this version. So we don't lose neither x nor y. And we can still recover the old sec by projecting, however this projection won't be linear anymore. Now, what I was on previously is that if you have a if you have a normal function, the more arguments you have, the more powerful the function is. If you have linearity, an argument can be a liability, and you need to somehow take care of it. You cannot just ignore it. And this means that functions are less powerful. But on the other hand, if you make a system less powerful, then it can be interpreted in a different way. So a normal Haskell value is like information, and information is in a sense worthless, in the sense that it can be duplicated, it can be ignored. So there is, it's a bit like, it is not precious. But with linearity, you cannot do this. So you can interpret values no longer as information, but as resources. Let's write a few functions to get acquainted with this. Let's write application. The normal application operator in Haskell is apply fx equals fx. And how do we call it normally?
Space. Or $.
That's the dollar, yeah, right? Mm-hmm. I can convert a linear function to an unrestricted function this way. However, linear functions are not a subtype of normal functions, so I cannot say this. Okay. So there is no casting of linear values to unrestricted values. You have to explicitly reconstruct a new function that calls the linear function. There is no subtyping because this causes problems. This method of converting is called eta expansion. You add an extra argument to both sides.
Sorry, can you go back to the error? Can you produce the error?
Oh, so the error messages are horrible,
and
and
I
I
want to know why they
yes.
say 1 omega.
I'll explain. I'll explain 1 omega later. Yes. However, yes, the error messages are poor quality, and we hope that this will be improved before the final release. So the state is that we are planning to merge linear types to GHC 8.10. Remember that 8.8 has not been released yet. However, it's in feature freeze. And a long time ago, GHC had an extension called polykines. But the first version that had it released, it had several bugs. The feature was kind of usable, but the priority was not to break programs that do not use this feature. And linear types are a pretty huge extension, even though it seems to be we are only adding one type, but we are modifying what does it mean to be a function in a language where functions are almost everything you do. So it's a pretty huge internal change, even though on the surface it's only adding one symbol. And I will talk about implementation later. For now, our priority is not breaking anything that uses that does not have linear types enabled, so backwards compatibility, and delivering delivering a basic version. However, error messages might be poor, and you might be forced to write programs in a more awkward way than you would have to do than you could with normal version. Okay, if you'd like to use a tuple in a linear way, you can pattern match on it and consume both x and y in a linear way. So what I can do is I can say swap xy equals yx, or I can say swap, or I can refuse to swap. I can just say swap x. However, I cannot do this. I'm then getting some error regarding mentioning multiplicities. If I like, I can flip. And this is linear too. Furthermore, if only one of the argument of the function is linear, then flipping will enforce that linearity is preserved. So if I say that b here is not linear, then this refuses to compile, and I have to make this b linear. Some examples of nonlinear functions. If I'd like, this is the first function. If I try to make it nonlinear, it won't work. If I write the if then else function, this one works because I didn't use linear arrows. If I try to use them, I'm getting an error. If then else is linear in the Boolean. You can write a linear function that takes a Boolean by pattern matching on true and false. Since Booleans do not have fields, this is everything you need to do. With tuples, we had to consume linearly the elements of the tuple. Lists. If you'd like to consume linearly a list, you need to pattern match on it and consume all fields. So I can say add and addition is linear in both arguments.
So having a non-polymorphic, having a concrete type as an argument and making it linear enforces that I do a total pattern match on that argument, right?
No. If a function, if I can do this, and this is still linear. Okay? So linearity applies only if your function terminates. If it doesn't, then in a sense you are fulfilling the promise because your function is not consuming the argument non-linearly. So as I gave earlier an example of a looping function that was linear, even though it couldn't be.
And when you say consume, is it consuming just calling the regular function?
So by consuming, I mean we look at the right-hand side of the function definition, and to consume an argument linearly, you can return it unmodified, pass it to a linear function. If the argument is a function, you can call it and then consume the result of this call linearly. If the argument is a data type, you can pattern match on it and consume all fields linearly.
But the match doesn't have to be total.
The match doesn't have to be total. If you just raise an exception, this is a perfectly valid linear function. Furthermore, you can combine those methods. So you can first pattern match on an argument on a tuple, and then pass one of its components to a linear function. Then if it's a function, you can call it, and so on. What you can do is you can't do those things in parallel. So if I give you x, you cannot simultaneously pass it to a linear function and somewhere else call it. Linearity is like all types an over approximation of reality. So if I have this const function, and if I try to define a linear function f that is const xx, well, this refuses to compile. However, if I simplify this to just saying x, it will. And this situation is similar to the type system. If I say that f is a character and f is equal to if true then a L0, well, in runtime this code would work, right? But it's true. But a type system is just an over approximation, and we want a static guarantee that the type is correct. Likewise here, we'd like a static guarantee that a function is linear, and if we call a nonlinear function, that it doesn't matter what is the runtime behavior. We want it to work on in the static way. Okay, so I gave you a few examples, and those were all definitions of functions that are already there, except we had to repeat them because they have a different type. In linearity, there is another function constructor. It is a multiplicity polymorphic arrow. What I can say is applying is multiplicity polymorphic in M. What does this mean? M is here a multiplicity. M is a multiplicity, and multiplicity is defined as either 1 or omega. The multiplicity 1 means linear, and the multiplicity omega means nonlinear. So this is a normal function. The multiplicity omega will probably be renamed to many, and this syntax, we won't use this syntax. It's just because the prototype needs, we need an easy way to parse things. Okay. So
just does that arrow type encode at least once?
there is no arrow that encodes at least once. The general omega arrow can do anything, and this is this arrow. And the one arrow means you encode exactly once.
But the two okay.
So if so, this type T is available in GHC prim currently under the name fun. If I declare type f1 equals fun of 1, and I probably need to turn on data kinds. This is fun 1. If I say f omega, you can notice that fun omega is just the normal infix arrow. So, sorry. Let me expand on this part a bit more. If you look at the right-hand side of a function, what you can say is, let's define a kind of a function, how many times x. If you have an expression x, then you are using it only once. If you have a lambda, a, and then something, then it's as if saying how many times. If you have a function application, and this function has type f, it has multiplicity mb, then this multiplicity, then the amount of times you use x here is equal to how many times occurs in f plus m times how many times x occurs in this x. So I'll rename this to y. If it's just a constant or a different variable, we say that a variable is unused. So there is a kind of an algebra on multiplicities, and while the prototype currently does not have it, there will be multiplicity functions such as that will allow you to write polymorphic functions that call mult_add. I will give you a few examples later. Okay, here's a question. Is the filter function linear?
No.
The second argument.
If the list is empty, then it's not used. The function isn't used.
So let's try writing filter. Alright.
So it doesn't seem linear. First of all, we are pattern matching unless the if is translated to a pattern match. I mean, I don't know.
So you can consider this to be a pattern match in f of x.
We're also using x more than once, right?
We are using x more than once. That's one problem.
And f is potentially not used in the first case.
Morally, we are going to ignore some of the contents of access.
Right. So that's the issue. So filtering cannot be made linear. Now, a different pattern would be a partition function.
That could be linear.
Right. So partitioning, we case f, we check whether fx is true. If fx is true, then we let me make it this way. So, do you see a problem now?
Yeah, at the end of the line, before access, you need f.
Partition f x's.
All right.
So we're still using each x more than once in the check and once in the output.
Right. So this is a problem. This partition function is not linear, and the way you can make it linear is by threading this x. So what we will do is we'll return this predicate. Will check the property, but then it will return the argument unmodified. And furthermore, we have to say that this predicate is linear. So this time we can't just say if f of x. We need to pattern match on fx, and we'll get either true, and then we return x prime y as cs, or we get false. Okay.
Can you actually construct this predicate linearly?
Yes.
And don't we need more linearity annotations? I mean,
Right. So we need to add linearity in annotation. So we are not linear in this function because we are calling it multiple times each for every argument. We are linear on this list. However, we now run into a small limitation of this prototype. Namely, you cannot use case statements in a linear way. What you have to do is you need to define a helper function. So likewise with lets.
Is that a limitation or just something that hasn't been?
This is only something that has not been implemented. We plan to fix it later. So I need to say is h of partition f xs yes. And now let's define the function h. So if we have true, then we can say x prime y as cs. If we have false, yes. One more thing is that linearity is not inferred. So every time when you define a linear function, you need to give a type signature.
in principle?
Yes. However, the prototype is not doing this. And this works.
I didn't see how to construct the predicate function. If it has to test its A, that's...
Right. So you can do it with arbitrary A, but with an arbitrary A, there is also no way to get a boolean. You need to use a specific A. So for example, if this A was just booleans, then you can pattern match on that. Right? So you need to, in a sense, to pattern match on this A, and you could recreate it.
Can you actually rate one of those functions, like check whether an integer is even or something? worth to see? Is it,
Hmm.
There has to be some case where we can do it if this function is useless, right?
Right. So, well, what I can say is Boolean. Is that good enough?
But that's just for time.
You have to implement is even to return
Yes,
integers.
you would have to implement is even, and that would mean that we need a different library on integer operations. And currently there is no such library, so we will have to add new operations to GAC prim and make them linear. So this is doable, and I will be talking later about techniques you can get it.
So are there other types besides bool that we can do this with?
Well, any algebraic data type, like a list. What you can do is the primitive integer type or a float type, because they are defined in a special way. Likewise, similar situation happens when you try to write a sort function. The normal sort by function takes two a's and returns an ordering. So we can't make this linear, but what we can do is we can say, right? And this function can be made linear. Now I understand this is a bit complex, so that the function has to return its argument. There is a pattern called borrowing that we might add in the future that will make this simpler.
So like we pick on the argument but don't consume it, right?
Something like that, yes.
Can you do the same to linearize the function by returning the function itself from itself? So we took two arguments a and returned them in tuple. Can we do the same with function to make it linearizable?
I don't understand.
Okay, in partition we don't have our first argument linearizable, right?
Right.
Can we do it linearizable by returning the function from itself, as we did with first argument of this function?
Well, you could define a data type that does that. What I would do is you could zip all those functions, right? If you have it, if that function is really, if the function can be really recreated many times, then that function doesn't need to return itself. You can just make it an unrestricted argument. So the goal is not to make everything in Haskell linear, because we can't do that. Instead, it's to make only a few functions linear and use it when creating libraries.
Can you explain why we try to use invariant exiting once instead of at most once?
Right. So using
so much easier.
Right. So doing this is so we are creating a less powerful system, but again you get more guarantees from it. If you'd like to say that a function either drops the argument or uses it linearly, you can return a maybe. Right. So. Sorry, you can take a maybe. Okay, never mind. What about the mapping function? Out. Can you make linear?
With regard to the list? No.
You need your.
Right. So if the mapping function is linear, then the function, if f is linear, then map f is linear, right? And this is a nice case for polymorphism, because we can say that if this function has multiplicity m, then this function has multiplicity m.
Do you need to pull out a helper?
That's good. Okay, I did something wrong, but I don't know yet what. Is this because I'm surprised.
How does function is linear if you use multiple times?
So, oh, this is a good question. So the f function is linear, but this function is linear, but the argument to map f is not linear, right? And I can't make this f nonlinear, because this f could duplicate this argument a, and in this case I would be duplicating the list a elements of this list a, right? So if I have the dot here, I need the dot here.
So can you talk about some of the benefits that using linear types gives us, or which fields we would want to do this?
Yeah, I have a section of applications,
Okay.
but it's much later, yes.
Well, one question. This multiplicity parametric polymorphic form can be fixed as something that is neither 1 nor omega.
Currently,
2, 3, 4.
so currently we only have two multiplicities. 1 and omega.
1 omega.
We could potentially have a zero multiplicity for a function that does not use the argument at all. And type arguments are are those kind, because types are erased at runtime, so it's as if they were not used at all.
Yes.
However, the addition of zero multiplicities complicates some internal things, so we don't have it yet. And we will see what multiplicities we'll have in the final version. The goal here is to have only a few, but the system should be extensible, so that we can add more multiplicities later.
Extensible in a plugin GHC form, or extensible
So as in the first version that we'll release, we'll have just 1 and omega, and if there will be demand for more multiplicities, we might add them. The most obvious candidate is 0, or the affine multiplicity, which would be either 0 or 1. Okay, let's talk about constructors. Normally in Haskell I can create a data type like this, and the question is this linear? So constructors are functions, and they can be linear or non-linear, and you can't see it using this syntax, but you can rewrite the data type using a different syntax, the GAT syntax, in this way. Now if you don't know the GAT syntax, it's just the same, this and this mean the same thing, except here we make the type of MAC-T explicit. By default, if you use this syntax, every constructor will be made linear. So MAC-T will be a linear function. And this makes sense because linear arguments are generally more useful than unrestricted arguments. It's harder to use unrestricted arguments if you like to write a linear API, and if you're writing a general API, you can always forget about linearity. If you use the GAT syntax, you need to be explicit. This will be a linear data type, and this will be an unrestricted data type. There is one more piece missing here. If I define this data type or this data type in a code that does not use linear types. Then we have a backwards compatibility problem. If someone will fully apply this MAC-T, it's not an issue because linearity will be lost. But if they will try to pass MAC-T to a higher order function, well, there will be a type mismatch. You cannot pass a linear function you cannot pass a linear function and cast it implicitly to a general function. So the solution is multiplicity polymorphism. If you define a type using this syntax or this syntax, MAC-T becomes implicitly generalized to a multiplicity polymorphic function. So MAC-T becomes AMTA. So let me repeat here because there are several. This is a bit complicated. We write this type in a Haskell 98 code, in a Haskell code that does not linear types. It is considered to use a linear argument. The next step is that we generalize it to a multiplicity polymorphic function. And the final step is that if you write a multiplicity polymorphic function and you don't have linear types enabled, so you import an API that was made to work with linear types, but you are not interested in linearity at all, everything becomes omega. So if you add those three steps together, yes, constructors are linear, but end users who are not interested in linear types do not see anything at all. Okay, I think we'll take a break here.